Okie dokes. So there are a few properties that are associated with ionic compounds. Ionic compounds we know from experimentation to have, first, high melting points. What is melting point? Well, melting point is what we call the temperature at which a solid becomes a liquid. So a common example is water. Ice turning into water. Now ice melts into water at 0 degrees. So we say the melting point of ice to water is 0 degrees Celsius, which is not very high compared to ionic compounds. So ionic compounds, if we say are to have high melting points, it must be very high. So just as an example, sodium chloride has a melting point, I need to check this, melting point of about 800 degrees Celsius. So it's a solid all the way up until 800 degrees Celsius, whereupon it becomes a liquid. So that's a testament to how high the temperatures must go before an ionic compound will become a liquid. I want you just to link back to a previous idea that we explored, magnesium oxide, where magnesium. It's worth noting that the magnesium cation that forms this is a 2+ cation, and the oxide anion that forms this is a 2- anion. I mentioned how this 2+ charge from magnesium and the 2- charge from oxide lend itself to give us a much stronger bond. So this much stronger bond should translate to the properties of this ionic compound. So if sodium chloride with a 1 positive and a 1 negative charge on the sodium and chloride has a melting point of 800 degrees, and what then would be the melting point of magnesium oxide? So I think a quick Google search would show you that this compound here should, and it really should, have a higher melting point than sodium chloride. So let's keep going along. The second point now that we're going to look at, gets me some more space, is that they have high boiling points. This makes sense. So if they have high melting points, they would have much higher boiling points. Now, boiling points is properly defined as being the temperature by which a compound or a substance, transitions from being a liquid to a gas. So the temperature where a substance transitions from a liquid to a gas. Now, I'm not really going to look at some numbers, but you can see for yourself to see the temperatures at which certain ionic compounds would transition from being liquids to gas. Okay, now third property is that they are brittle. Brittle. Now, what does brittle mean? Well, brittle means they break. They break easily when given enough force. This is the opposite of malleable, where if you give enough force, instead of breaking, the material will bend. Now, there's a good reason why ionic compounds are brittle, and I'll try to illustrate this. It's quite a tricky concept. So let's imagine our lattice for our ionic compounds. Now, if you don't know what a lattice is, just watch another video on the structure of ionic compounds. Hopefully that'll get you up to speed with what a lattice is, what an ionic lattice is. So this lattice here lends itself to a few of the properties that we observe with ionic compounds. Now, I didn't explain the melting point, a high melting point in terms of this lattice, but you can imagine that because these ions are all like very strongly linked with each other, like positive ions are all being surrounded by negative ions, and negative ions are all surrounded by positive ions. This interlocking network of ions is very strongly held together, which leads to high melting points and so on. But why are they brittle? So why do they break easily when they're given enough force? An example of an ionic, a substance that's made up of ionic compounds, is ceramic. So if you have the old traditional Chinese teacups or that kind of stuff, those break very easily if you were to drop them on the floor, because they're made up of ionic compounds. So they won't break too easily if you just, flick them with your finger or tap them lightly on the table. But if you were to hit it with enough force, drop it onto a hard surface from a considerable distance, they will break. Now, why is that so? Let's have a look. Now, I'll redraw this lattice because I think to illustrate this concept, I need to space out these ions just a little bit more. Just bear with me. Okay, so imagine we apply some force. So I'm going to draw a hammer to illustrate this. So this hammer here knocks this ionic compound, and it basically shifts these two layers along. I'm going to shift these two layers along. Let's see if this works. Perfect. So after knocking these two layers here with an external force, they shift along. Now, what do we see here? What's the result? Perhaps you notice that the negative charges here are aligned. These positive charges here are aligned. And do you know what like charges do when they're close together? A bit like if you were to put a magnet, like the two same colored ends or same kind of ends opposite each other, they would force each other apart. Same with these charges here, they all force each other apart. And in this forcing apart of the layers is where we get the breaking of the substance. So they're brittle for this reason. If you give them enough force that you shift the layers along, they will very, very quickly and very easily separate from one another.